Okay, we're going to take a look at volumes of rotation. So you start off with some flat figure, you rotate it around an axis, and through that rotation create a 3D figure, create a volume. So we'll actually just start with an example. Let's go with a triangle, and we'll draw that triangle on the XY axes. And then if we imagine rotating that triangle around the y-axis, so this is the center of rotation, and I rotate this triangle around, that would be to 180 degrees, and then it would go around the back, and you would make a cone. And you'll notice that if you cut across anywhere here, all those cross sections would be circles. And each cross section has an area of pi r squared. But in this case, our r is f of x. So if you have your x value here and you go up to f of x, that gives you your r value. So your area is really pi and your radius is whatever your function is, whatever this function is here, squared. That just means that if you have a more complicated function, if this makes some kind of squiggly line, that might not be a great function, but if it makes a bit more complicated line, then that's what gets rotated around. You don't end up with a cone, but you end up with this idea of rotating those cross sections around. And of course, it will still be a circle, no matter how complicated f of x is as it gets rotated around. So when we go and calculate the volume is the sum of all of these cross sections. So when we do sums, we're saying, well, we integrate our to find the volume, we take the integral of from a to b, and in this case the area formula, which is pi f of x squared with respect to x, and this is known by doing this, by creating cross-sections that are all circles and essentially just adding up all of these little disks, all of these circles. This is known as the disk method. And it can be slightly simplified by bringing out the pi and being left over with f of x being squared dx. So let's take an example of this and take a closer look. I'm going to calculate the volume of the solid that gets obtained by rotating the region under y equals x squared. So here's a picture. Here's y equals x squared. And there's your y-axis, your x-axis, and we're going to rotate that about the x-axis. So when you rotate this around, it'll end up coming down this way, like this, and it'll be a circle that rotates around, and so will all of these. So it forms, kind of looks a little bit like a sideways tornado. It forms all those circles. It's a volume though, so it's not hollow. We're filling it in, and it's from 0 to 3 that we're doing this on. So when we go and set up our formula, we use the volume and pi. We're going from 0 to 3, and our formula is x squared with respect to x. And so you get pi from 0 to 3 of x to the 4th dx, which is pi x to the 5th evaluated between 3 and 0, divided by 5, of course. And so you get 3 to the 5th, and 3 to the 5th is 243, times that pi, divided by 5, take away 0, you don't need that. And that is the volume. So this is in units cubed. I'm not sure what the units are, but in units cubed. We can create what are called pipes or rings by removing the inner part from an outer part. So it looks something like this. Let's say we had a couple of functions. We've got f of x and we've got a g of x function here as well. If you rotate g of x around the x-axis, you'll end up with a pipe like this. And if you do f of x around the x-axis, bulges out a little bit here, comes in and goes back out, you end up with something like this. And if you were to want to calculate the volume and pretend it's a hollow tube. So you've got this outer one, take away the inner one. That's not that hard of a thing to do. Imagine taking any cross-section of this. What you would get as a cross-section is a circle take away a circle, a very thin ring, as it were. So that's kind of cool, and it's fairly easy to calculate the area of a circle take away another circle. And we can put that together into a formula that will allow us to calculate volumes of these like pipes or rings. So yeah, any cross-section is a circular ring known as an annulus or a washer, and the total volume is pi, and you go from A to B, so however far across, like maybe from here to here, that would be A to B, and then your function is just a subtraction of what is your radius of your outer, or what is the formula, f of x of the outer function, and that's got to be squared. And then you subtract away the radius function for the inner, the one that's smaller, like your g of x in this case, squared with respect to x. And that can also be written, as I've alluded to, that it's from a to b of whatever the outer function is squared, take away whatever the inner function is squared with respect to x as well. Occasionally outside of my room, 133, there's a display of how this is used, so you're welcome to go take a look at some of those examples made by past classes. And there's a fantastic demo in the online textbook that also shows the rotation of this. It's example 4, and it shows the difference between creating questions that need the disk method and questions that need this washer or ring or annulus method with subtraction. The actual calculations are the same as we've been doing before, so I'm going to leave it here and come to class ready to practice a couple of these.